atomic, and molecular masses. Every atom of an element consists of fixed number of protons, neutrons, and electrons, the subatomic particles. The number of protons varies from atom to atom. The mass of the atom changes as the number of subatomic particles is changed. Hence, masses of different atoms of different elements are different. The size of single atom is of the order of 10 raised to minus 15 meter, and the mass is of the order of 10 raised to minus 27 kilograms. Hence, it is not possible to weigh a single atom. However, it is possible to determine masses of the atoms of the elements relative to mass of some standard element experimentally, using mass spectrograph. The standard element chosen is assigned appropriate value of mass of atom. By international agreement, in 1961, for determining atomic masses, carbon-12, a distinct atom of carbon was chosen as standard with its atomic mass. 12, atomic mass unit, abbreviated as AMU, and defined as 1 upon 12 of the mass of an atom of carbon-12, equal to 1.6605 multiplied by 19 raised to minus 24 gram. The masses of all other atoms are determined relative to the mass of an atom of carbon-12, the standard. Recently, the unit of atomic mass, AMU, is replaced by U, meaning unified mass. Using mass spectrograph, atomic masses of different elements were determined. It was found that atomic mass of hydrogen is 1.00 U, that of carbon 12.011 U, and that of iron is 55.85 U. Careful investigation of mass spectrograph shows that natural hydrogen contains 3 isotopes of hydrogen in a definite proportion, so that the observed atomic mass 1.00 U. Similarly, carbon contains 3 isotopes C12, C13, and C14, so that the observed atomic mass is 12.011 U. Average atomic mass. Isotopes are the atoms of the same elements, having same atomic number, containing same number of protons and electrons, but different number of neutrons, hence possess different mass numbers. Many naturally occurring elements exist in the form of 2 or more isotopes. The observed atomic mass of the atom of the element is the average atomic mass of the elements, taking into consideration the natural abundances of the isotopes. The natural abundance means percentage occurrence. The mass spectrometer, with higher precision, shows variation of exact atomic mass of the isotope of the elements, with its relative abundance. With the help of Aston's mass spectrometer, it was proved that neon exists in nature in the form of mixture of 3 isotopes. 1. Neon 20, with atomic mass 19.9924 U. With natural abundance 90.92%. And 2, neon 22, with atomic mass 21.9914 U. With natural abundance 8.82%. 3, neon 21 with atomic mass 20.9940 U. With natural abundance 0.26%. From this data, it is possible to calculate observed atomic mass of neon in terms of average atomic mass. Average atomic mass of Ne is equal to atomic mass of Ne20 multiply by percent of Ne20 plus atomic mass of Ne22 multiply by percent of Ne22 plus atomic mass of Ne21 multiply by percent of Ne21 upon 100 is equal to 19.9924 U. Multiplied by 90.92 plus 21.9914 U multiply by 8.82 plus 20.994 U multiplied by 0.26 upon 100 is equal to 20.1707 U. Problem 1.1. Lithium exists, in nature, in the form of two isotopes, Li6 and Li7, with atomic masses 6.0151 U and 7.0160 U, and the percentages 8.24 and 91.76 respectively. Calculate average atomic mass. Solution. Average atomic mass of Li is equal to atomic mass of Li6 multiply by percentage plus atomic mass of Li7 multiply by percentage upon 100 is equal to 6.0151 U multiplied by 8.24 plus 7.0160 U multiplied by 91.76 upon 100 is equal to 6.934 U. Problem 1.2. Chlorine has two stable isotopes, Cl35 and Cl37, with atomic masses 34.968 U and 36.956 U, respectively. If the average atomic mass is 35.452 U, calculate the percentage abundances. Solution. Let the natural abundance of Cl35 isotope be X%, and that of Cl37 be 100 minus X%. Hence, average atomic mass is equal to atomic mass of Cl35X plus atomic mass of Cl37 multiply by 100 minus X upon 100. 35.453 is equal to 34.968X plus 36.956 multiply by 100 minus X upon 100. X is equal to 75.60. 100 minus X is equal to 24.40. Hence, natural abundance of Cl35 is 75.60%. Molecular mass. Molecule of a substance is also very small, like an atom. And its mass is also small, of the order of 10 raised to minus 26 kilograms, which is not convenient to use. the molecular mass, is also expressed as a relative mass, compared to mass of standard atom of carbon-12. Molecular mass of a substance is defined as the ratio of mass of one molecule of a substance to 1/12 of mass of one atom of carbon-12. It is also the algebraic sum of atomic masses of constituent atoms, which constitute the molecule. Molecular mass is also expressed in AMU. It is a number that indicates comparative mass of a molecule of a compound, with respect to 1/12 of the mass of one atom of carbon-12. Gram molar mass is the molar mass expressed in gram. 1 gram molar mass, also called 1 grand molecule, or 1 gram mole, or simply 1 mole. 1 mole of the element means amount of the element equal to its atomic mass in gram, and also called 1 gram atom of the element, or 1 mole of the element. Avogadro's law. Gay-Lussac's law of combining volumes of gases was stated in 1808. Simultaneously, in the same year, Dalton proposed atomic theory. Avogadro, in year 1811, combined Gay-Lussac's law and Dalton's theory to propose Avogadro's law. It states that equal volumes of all gases, under identical conditions of temperature and pressure, contain equal number of molecules. Avogadro introduced the idea of molecule as the smallest particle of a compound. Dalton believed that compounds are formed when atoms of different elements combine in a fixed ratio. It was firmly believed that the atoms of the same element do not combine to form a molecule. Avogadro suggested that most of the gases do not exist in the atomic state, but exist as polyatomic molecules. Like diatomic hydrogen, H2, diatomic oxygen O2, nitrogen N2 or chlorine Cl2, etc. These diatomic molecules take part in the reaction, as atoms do not exist in free state. That was the most revolutionary idea. Avogadro's hypothesis was published in French journal, Journal de Physique in 1811. The idea suggested by Avogadro was totally neglected by scientist community for over 50 years. The idea of existence of a pure element as diatomic molecule was difficult to digest. Finally, in 1860, in the first International Conference on Chemistry, held in Germany, Stanislaw Cannizzaro explained the importance of Avogadro's hypothesis, and only then the precious work was recognized. Mathematically, Avogadro's law is stated as, at constant pressure and temperature, volume of a gas is directly proportional to the number of molecules. V is directly proportional to the number of molecules, where pressure and temperature constant. But number of molecules is directly proportional to the n, the number of moles of gas. Hence, V is directly proportional to n, or V upon n equals constant, where number of moles, n, equals mass of gas, upon molar mass of gas. At STP, it may be possible to calculate volume per mole. V upon N of an ideal gas. According to general gas equation, PV equals nRT. Hence, at STP, V upon N equals RT upon P, where R equals 0.08205 liter atmosphere, per moles, per Kelvin. V upon N equals 0.08205 a liter atmosphere per moles per Kelvin into 273.15 Kelvin upon 1 atmosphere equals 22.4141 liter per moles. Hence, the volume of 1 mole of any pure gas at standard temperature and pressure is always constant, equal to 22.414 liters or 0.022414 cubic meters. Atomicity of a gas molecule. Atomicity of a molecule is the total number of atoms of constituent elements combined to form a molecules. Consider the formation of hydrogen chloride from hydrogen and chlorine. Hydrogen and chlorine do not exist in free atomic state, but exist in molecular state, and molecules take part in the reaction. The reaction may be written as hydrogen plus chlorine gives to hydrogen chloride. According to Gay-Lussac law, 1 volume plus 1 volume gives 2 volumes. According to Avogadro law, V is directly proportional to N. N molecules plus N molecules gives 2 N molecules. Dividing by N, 1 molecule plus 1 molecule gives 2 molecules. Dividing by 2, 1/2 molecule plus 1/2 molecule gives 2 molecule. This implies that 1 molecule of hydrogen chloride is obtained from 1/2 molecule of hydrogen and 1/2 molecule of chlorine. If molecules of hydrogen and chlorine are monoatomic, 1/2 atom each of hydrogen and chlorine react to form 1 molecule of hydrogen chloride. This means atoms are divisible. This is contrary to Dalton's law, according to which an atom is indivisible. Therefore, it is not possible to have 1/2 atom of each hydrogen and chlorine to synthesize 1 molecule of hydrogen chloride. This conflict is resolved by considering that hydrogen and chlorine does not exist in free state as atoms but exist as diatomic molecules. So, that a molecule of hydrogen chloride is formed from 1/2 molecule each of hydrogen and chlorine. The reaction is represented as 1/2 H2 gas plus 1/2 Cl2 gas gives HCl gas. According to Gay-Lussac law, 1 volume plus 1 volume gives 2 volumes. According to Avogadro's law, X molecules plus X molecules gives 2X molecules. Dividing by 2X, 1/2 molecule plus 1/2 molecule gives 1 molecule. 1 atom plus 1 atom gives 1 molecule. Hence, 1 molecule of hydrogen or chlorine contains 2 atoms of each. This is in agreement with Dalton's atomic theory. The reactions represented diagrammatically in X molecules of hydrogen plus X molecules of chlorine equals 2X molecules of hydrogen chloride. 1 volume, plus 1 volume, gives 2 volumes. Mole concept and Avogadro number. The mass of a single atom, of an element, or single molecule of a compound, is negligibly small, and it is difficult to weigh. The quantity of a substance, equal to its atomic mass, or molar mass in gram, is referred as 1 mole of the substance. 1 mole of the substance is defined as the amount of substance that contains the number of particles, atoms, molecules, ions, or electrons etc. as present in 0.012 kilograms of carbon-12. This number of particles is determined to be equal to 6.022 into 10 raised to 23 particles. The number 6.022 into 10 raised to 23 per moles is called Avogadro number N. A. This is the number of atoms, molecules, ions, electrons present in 1 mole of a substance. This number of electrons makes an electrical charge of 1 Faraday. 1 mole of different gases, having different molar masses occupy same volume, of 22.414 liters, and contain 6.022 into 10 raised to 23 molecules, is illustrated, as shown in the above figure. The relationship between mass of gas, with number of moles, volume of gas, at STP, and the number of molecules, are given by mole triangle, as shown in the above figure. Following relationships are important while attempting numerical. 1. Number of moles. N equals mass of the substance, upon molar mass of the substance. 2. Number of molecules, equals, N into Avogadro number. 3. Volume of gas, at STP, equals, N into 22.414 liters. Calculate the number of moles, and molecules, present in 0.032 milligrams of methane, C equals 12, H equals 1. Solution. Molar mass of methane, CH4, equals 12, plus 4, equals 16, gram per moles. 16 grams of methane equals 1 mole. Therefore, 0.032 milligrams equals 3.2 into 10 raised to minus 5 grams, methane, equals 3.2 into 10 raised to minus 5 upon 16 mole, equals 2 into 10 raised to minus 6 mole, methane. Now, 1 mole of methane equals 6.022 into 10 raised to 23 molecules of methane. Hence, 2 into 10 raised to minus 6 mole of methane equals 12.044 into 10 raised to 17 molecules of methane. Calculate the number of moles and molecules of sulfur dioxide obtained by combustion of 6.4 into 10 raised to minus 2 kilograms of sulfur. S equals 32, O equals 16. Solution. The balanced chemical reaction for combustion of sulfur to sulfur dioxide is given below. S plus O2 gives 2 SO2. Hence, 1 atom of sulfur produces 1 molecule of sulfur dioxide. Molar mass of SO2 equals 32, plus 32, equals 64, gram per moles. Number of moles of sulfur equals mass of sulfur upon molar mass of sulfur. 6.4 into 10 raised to minus 2 kilograms upon 32 into 10 raised to minus 3 kilograms per mole equals 2 mole. Hence, 2 moles of sulfur on complete combustion will produce 2 moles of sulfur dioxide. 2 moles of SO2 equals 2 into 6.022 into 10 raised to 23 molecules of SO2. Hence molecules of SO2 equals 1.2044 into 10 raised to 24. Calculate the mass of one oxygen atom. An oxygen molecule, in kg. O equals 16. Solution. Molar mass of oxygen atoms equals 16 grams per moles. 6.022 into 10 raised to 23 atoms of oxygen equals 16 grams of oxygen. Therefore, one atom of oxygen weighs equals 16 grams upon 6.022 into 10 raised to 23 equals 2.657 into 10 raised to minus 23 grams equals 2.657 into 10 raised to minus 26 kilograms. Oxygen is a diatomic molecule. Hence, mass of one molecule of oxygen equals 2.657 into 10 raised to minus 26 into 2 equals 5.314 into 10 raised to minus 26 kilograms. How many oxygen molecules are needed to synthesize 0.245 grams of carbon monoxide by controlled reaction with carbon? Solution. The balanced reaction is given as 2C plus O2 gives to 2CO. 2 into 12 grams 2 into 16 gives to 2 into 12 plus 16. That is 24 grams. 32 grams gives to 56 grams. Hence, 56 grams CO equals 32 grams of O2. Therefore, 0.245 grams CO equals 0.245 grams into 32 grams upon 56 grams equals 0.14 grams oxygen gas. Now, 1 mole that is 32 grams O2 equals 6.022 into 10 raised to 23 oxygen molecules. Therefore, 0.14 grams equals 6.022 into 10 raised to 23 into 0.14 grams upon 32 equals 2.634 into 10 raised to 21 moleculars. Calculate the number of moles, molecules, and total number of atoms present in 1. 1.1 into 10 raised to minus 4 kilograms CO2. 2. 5.6 cubic centimeters of ammonia at STP. And 3. 0.4 grams of helium gas. C equals 12, O equals 16, N equals 14, H equals 1, and He equals 4. Solution. 1. Number of moles, N, equals mass of CO2, upon molar mass of CO2. Molar mass of CO2 equals 12 plus 32. equals 44 grams per moles. Equals 44 into 10 raised to minus 3 kilograms per moles. Hence, N equals 1.1 into 10 raised to minus 4 kilograms. Upon 44 into 10 raised to minus 3 kilograms per moles. Equals 2.5 into 10 raised to minus 3 moles. Number of molecules of CO2 equals number of moles into Avogadro number equals 2.5 into 10 raised to minus 3 into 6.022 into 10 raised to 23 equals 1.505 into 10 raised to 21 molecules. CO2 gas is triatomic. Hence, number of atom present in 1.1 into 10 raised to minus 4 kilograms of CO2 equals 1.505 into 10 raised to 21 into 3 equals 4.515 into 10 raised to 21 atoms. 2. Volume of ammonia gas at STP is 5.6 cubic centimeters. 1 mole of ammonia at STP occupies 22.414 cubic decimeters equals 22,414 cubic centimeters. Hence, 5.6 cubic centimeters will contain equals 5.6 cubic centimeters upon 22,414 cubic centimeters per moles equals 2.5 into 10 raised to minus 4 moles. Number of molecules equals 2.5 into 10 raised to minus 4 into 6.022 into 10 raised to 23 equals 1.5055 into 10 raised to 20 molecules. Molecule of ammonia, NH3 contains total 4 atoms. Hence, number of atoms in 5.6 cubic centimeters of ammonia equals 4 into 1.5055 into 10 raised to 20 equals 6.022 into 10 raised to 20 atom. 3. Helium gas is a monoatomic gas with molar mass 4. Hence, number of moles equals 0.4 upon 4 equals 0.1 mole of He. Number of molecules equals 0.1 into 6.022 into 10 raised to 23 equals 6.022 into 10 raised to 22. Numbers of atoms are also equal to 6.022 into 10 raised to 22, as if helium is a monoatomic gas.